So now we're going to do example 6.2 in your notes. This is the same system we were doing before, but now we're going to look at shear and then deflection. The first two items are shear and the second two are deflection. We're also going to take a look at if this beam had a notch out of it that leaves 9 inches at the extreme end. So it's what, 11.5-inch deep. This is the beam, not the joist. If the beam is 11.5-inch, so it's 2.5-inch notch out of here, and this is actual dimension of 9 inches. So same system. Remember, we have our joists running this way, and we have our beams running this way. So let's start with the joists. We had information already on these, and so the joist had a load. We ended up with 71 pounds per square foot. And the beams, we ended up with a load of 546, or I'm sorry, pounds per linear foot. BLF. All right. So we're going to take this and go from there. This will be, it takes shorter time in relation to what we've been doing. Okay. So beam, or sorry, let's do, oops, shear. Okay, so we're going to do the shear calculations for this guy. Let's start with the joist. Okay, so as I mentioned before, we can go out distance D. Both the joist and the beam that we're looking at have a uniform load on them, 71 or 546. So they have the uniform load on them, and if I look at just uniform load for shear, and you do not have to do pattern loading unless I mention to you that you should look at pattern live loading. The case here, we're going to use just the direct all the way across uniform loading. Now, I had said the code allows us to go out a distance D, or the height of the beam, from the support. So this is up to you. You can start here because it's easiest, and then move to here if you need to, or you can just start here from the beginning. For this problem, I'm going to go ahead and just do the top here and show you what passes or does not pass. And then if it doesn't pass, we're going to have to check at D. So let's go ahead and start out, and we'll just start with that one. So we know that here the reactions are WL/2 for shear. So this peak point is WL/2. This is my shear diagram, okay? So if I look at my joist from the previous example, I know what that number is for W. Gosh darn it. It resets with something I trigger that does that. Okay. The shear, WL/2, in this case, if we're just going to use the peak, now remember, this is conservative. That's why I can do this. So if it works, it works. If it doesn't, I'll have to refine a little bit. So 71 pounds per linear foot, 10 foot long, over 2, and I get a shear of 355 pounds. So my shear stress, the demand, or the demand side, VQ over IB equals 1.5 V over BD. Okay, you don't have to write this part out if you don't want to, because you can solve this. This is always true. This is the rectangular version. So just remember that if you're not going to write out that part of the equation. 1.5 times 355 divided by 1.5 times 7.25 for BD, and I get 49 PSI. So that's my demand, shear stress, capacity. I need to have the shear stress adjusted, and the C values here are C sub D, C sub M, C sub T, and C sub I. We have done, so all the values we already did for bending for the joist are the same, whether it's, are the same in shear. Okay, so we just have to look up F sub V. And when I look that up in the table, so just go back and look at this, the same table as the bending one. So I go back and I get F sub V prime equals 150 psi times 1, 1, 1, 1, because none of these were the factors that were above 1. And so I have the capacity side is equal to 150 psi. So 150 psi, I should probably keep in the same order, 49 psi is less than 150 psi, okay. Okay, so that guy, the joist is okay for shear. And the joist doesn't have a notch, so we don't have to deal with that. So joist is all good on this front. So let's look at the beam. So the beam, oops, the beam is you follow the same path that we just did here. And for the beam, B equals 546 pounds per linear foot times 12-foot span over 2. And that gives me 3276 pounds. Okay, that's the shear force demand, and the shear stress demand is 1.5 times 3276 over 5.5 times 11.5. And that gives me 77.7 psi. Yeah, that's my demand. Shear stress. Capacity side, F sub V prime, same idea. You look this up and you get 140 psi times, all these also end up to be 1. I get 140 psi. And so I've got 77.7 less than 140 psi. Awesome. Okay for shear. Now we do have to check the notch. So the next part of that problem was, let's go ahead and check the notch. So the notch, if you go in and look at the NDS, we talked about this just briefly before, 3.4, 0.3, 0.2 of the NDS, you will get an equation. And remember, when they check the notch, excuse me, when they check the notch, they check force, so shear force. And the equation they give you is V sub R prime equals 2/3 F sub V prime B D sub N. So D of the notch over D sub N over D squared. So this is in the NDS, it's equation 3.4-3. All right, F sub V we already did, 140 psi, we looked that up. D sub N is the depth of the notch, and they told us that that's 9 inches. So V sub R prime equals 2/3 140 psi. I'm going to leave units on just so I don't mess anything up here. B and D are 5.5 inches and 9 D sub N inches, so the area of this section here. And then notch depth over full depth, 11.5 squared, and I get a V sub R prime equals 2830 pounds. All right, so our demand, if we look back here, was in pounds, because we're going to use this guy when we're looking at notches, was 3276. So I've got 3276 pounds of demand. It's not less than 2830 pounds allowable, adjusted. Okay, so it was okay in shear until we got to the notch piece. And so the notch piece is not okay. So what do? Well, the first thing we do is see if it works if we actually use D out from the support, because that could make a big difference here. Um, it's a pretty big jump from 32 to 28, but let's see how it goes. If I checked it at D and it still didn't work, then I'm going to have to look at some kind of change to my notch, that I can't notch this beam as much as I did in this case. So I got to go back and look at geometry and see what I can do there, or I may have to move to a different member size so that I get the area here that I need. Okay, because if you notch too much, right, all you're doing is weakening this and shear at that notch. Out in the beam, okay, but out here at the edge, we've got to deal with the notch. Okay, so what I would say is let's go ahead and figure that out. So I don't actually have that written down in my notes, but we can do it. So you can probably, I'm going to derive the shear equation because I feel like people struggle with this. It's from structural analysis. But basically, how am I going to get this value, right? I can go look up the shear equation for a uniform load, but let's pretend that, we're engineers and we could do this pretty quickly. I'm joking, we're engineers. All right, I got a uniform load, W, for a length L. And you might remember it off the top of your head. Most people, well, the peaks and what we don't know, which is what we're used to, but we've got to go ahead and do this. And if you're in pre-stress, you wrote this equation and stuff for your spreadsheet. But where does this all come from? Never hurts to have a refresher, because statics is our friend and we can get this pretty quick. So we know those are WL over 2, right? W times L, some forces. This is symmetric, WL over 2. But I want to know what it is at a distance D. So I'm not just going to do it at D. I'm just going to do the generic version because that's how I can find the generic formula. Okay, so I know if I cut it right there, then I've got my shear and moment at that section. I'm not interested in moment right now, so I'm going to avoid that, but we are going to sum forces X and Y. So this uniform load would be the equivalent at a distance X of W times X, and then it would be acting in the middle of that piece. So sum forces Y equals 0. I've got W, oops, don't need any arrows on there. WL over 2, and coming down, I have WX, and I don't actually need to know where it's acting because I'm not summing moments, plus B, so V of X, so this is the V at whatever distance X. Okay, so V of X equals WL over 2 minus WX, so V of X equals W L over 2 minus X, which probably should look a little familiar. So this is the equation for shear at any point X along the beam, uniform load. So you can figure out any of these formulas for these beams because you can do statics, right? So just if the load is on one side or the other, you just have to be careful. But once you find the reactions, you can split it wherever you need it. Okay, and so I could have just made this a distance D straight away. But let's go ahead and use our formula. So V of X equals, well, go ahead and just do this. W L over 2 minus D. So V of X equals, what is our W? 546. 546. L over 2 is L, so 6 feet was 12 over 2 minus Our depth is 11.5 over, then they allow us to use that section. Okay, and they actually didn't even give us the length of the notch, which is interesting because the way they do this is just based on the cross section. So 11.5 inches, 12 inches per foot. All right, now I'm in pounds and feet. And I'm going to have to throw this in my calculator. Sorry. Clear. 11.5. I guess I don't need to walk you through that out loud. And I get 2753 pounds. Okay, so now let's try that. That is actually significantly less than 3276. So I was saying earlier, you can do the conservative way, and it's going to work probably for in a non-notch beam. It's probably going to work fine. You don't have to check or you can just save yourself the time and put it straight into. All I did was change this up for WL/2. I don't think it's that big a deal, and it saves you having to go back if you need to go back. So now I got 2753 is my demand, and that is actually less than 2830 pounds. So now I'm okay for shear. And I'm going to stop there, and then we will move on to deflections next.